Thanks for joining us today. I'm John Amond. I'm Professor of Chemistry Emeritus at Montana State University. I'm also President of MicroLab. Today I'd like to talk with you about energy of light and the terms that go with it: color, energy, and Planck's constant. And we're going to talk a little bit about how this works, and then we're going to do an experiment to determine the relationship between energy and color and frequency of light. Light is the language of atoms. Listen carefully and they will tell you who they are, how many are present, and if they're paired up with other atoms. The words used to describe light are color, wavelength, frequency, and energy. These four words and the quantities they represent are all interrelated. This experiment will help you understand these relationships. We can use a simple light-emitting diode as a probe to explore the relationship between energy and color, wavelength, and frequency of light. Light-emitting diodes emit light when enough energy is applied to them to cause an electron to jump from a lower to a higher energy level. In this model right here, light is given off when the electron falls back to its original position. The energy difference between the two electron energy levels is called the bandgap energy, and it's directly proportional to the energy in color and wavelength and frequency of light produced by the LED. We're going to use 7 different LEDs ranging from 470 nanometers in the blue to about 940 in the infrared to explore this relationship. There are 3 controls on this energy of light module. A rotary control selects the LED. Another rotary control sets the voltage applied to the LED. You can use the push button to record voltage and current when you've just begun to see light produced. You can see the magnitude of the current on this bar graph, and you can see the magnitude of the voltage on this bar graph.
No, you can.
Okay. I've set the switch to 640 nanometer LED, which is red. This is the current reading the voltage display here. I'm going to turn the voltage up, and I want you to watch. You can see the voltage indicator moving up here, and I'll watch the LED over here because pretty soon it's going to turn on. See, there it turned on, and as soon as it turns on, you can see its current go up on the left display. What we're really going to watch here is the light turning on right in the LED right here, and we're going to watch it on a graph. I'll start the graph running. I've got it set 640 nanometers. I'm going to start it graphing, and as I turn the voltage control up, you can see it move along the horizontal axis, and then all of a sudden it's going to start up. And if you were watching, the light just turned on right about then. So what's happening is, as we increase the voltage, right about here is the band gap, and then as we apply more voltage, current starts to jump across this, and light is being produced. And the way we check to find the band gap is to watch down in the LED and watch till it just starts to give off light. And I've got it set right there right now. It's not recording yet on the current meter, and you can see it on the graph. So let me push a button, and that's my red reading, and I've got a little bar graph that says red has this much energy right here. Okay, I'm going to switch up to yellow 602 LED. I'll move this up to 602. I'll start graphing, and I don't need that. And we're now going to run the yellow LED. Start graphing, and we're overshot just a little bit. Okay, there it is, and you see it takes just a little bit more energy to get started than the red. So I'm going to set it right where I can just barely begin to see light produced. Push the mark button, and now we have 2 data points. So I'll say okay. Let's go back to the 568. I'll move it up here. That should be a green, and I will start it graphing, and we'll run the voltage up and see what happens. Get it out here, and all of a sudden it starts to conduct, and I'll run it back till it's right at the band gap energy. I'll record that, and then I'll move it up to 502, which is kind of blue-green, and we'll match this on the chart here, and I'll say start graphing, and I'll run it across. And we need to watch carefully because this one gives off light pretty early, and I can see it right there. I'll run it past a little bit, back down, just giving off light, record it, and then we'll go up to 470, which is a blue, and I'll move that on the screen here, and we'll start graphing again, and I'll run it up here until let's run it up till it gives off a lot of light. Okay, and then I'm going to back off, and I'll watch the LED very carefully right here, and you can see it is just barely giving off light right there. And so I'll record that. Now, there's a bit of a generalization showing here. As you go from red to blue, it takes more energy to produce the light, and when you get that energy back from the LED, it's red or blue or whatever. Let's go down to the infrared. I'm going to move my switch down here to 880 nanometers, and I'll set this control to 880. Let's start graphing this. What do you think is going to happen here? This is a redder, if you will, light, infrared, and it takes less energy, quite a bit less energy. And so I'm going to just get that producing light, and I'll push the button to grab that point. And then let's try 940 nanometers. That's farther out yet. And I will start that going, and we'll see, there it is right there. And that's just starting to produce light. Push that button. Now, we've pretty much completed the experiment. Let's look at the data we have. Over here, I have a bar graph starting here at the infrared. And as we go infrared, red, yellow, green, or blue and violet, energy increases. Let me plot, instead of color, let me plot wavelength. And here we kind of have a curve going. A little hard to tell what's going on there. Curves are hard to tell, straight lines are a lot easier. Let's look at frequency. And here's something that says, hey, the energy here on this axis is related to the frequency almost directly. And the equation for that is here, y the voltage equals 3.68 and so forth. Let's change this number of energy from voltage to joules. All it'll do is give us a different reading here. And it says the slope is 5.86 times 10 to the minus 34th with a very small offset. The slope of the line relating energy in joules to frequency is called Planck's constant. So there are a couple of generalizations to look at here. One is qualitatively, as you go from infrared to red up to blue and violet, the energy of the light increases. The second one is the energy of the light here is directly proportional to the frequency, and the slope of that line is Planck's constant. In summary, let's look at two of these slides. The top slide says the energy of light increases as color goes from red to violet. The energy of light is directly proportional to the frequency of the light wave. That shows in the second graph. And the slope of the energy frequency graph is called Planck's constant. If you want to calculate frequency, the energy given off by electron transition of known frequency, that's how you do it.